we continue with this third algorithm to solve the task to find the increasing or the longest increasing subsequence with the spanned only or from n log n time. And I say that we need to use this array. It's the difference between previous algorithm and new algorithm. And we say that this array, we say initially that this array has very important property. Do you know what is this property of this array? Can you see to this definition and say what we can say about these two numbers?
Fix I is bigger than fix I minus 1?
Yes. And so we can say that there is invariant that fix is sorted array by increasing number. So it is interesting that it is sorted. So when we try to find subsequence that was interested for us, we spent n time to go through. Yeah, we remember that it's equal to n power n or multiply n, and we spent this time to find the longest subsequence. To find interested for us index of m. Interested for us index I think. And now if we work with sorted array, we can find it. Yeah. We can change it with log from n number, because we can use what we can use to find a number in the sorted array.
I can start from I.
For example, if we need, if we have array that has length equal to n and it is sorted, and we need to find a number in this array. No, not the biggest. Some number. Binary search, yeah. Binary search. And now we understand why this picture not so complicated and why we can use it to solve this task. For example, firstly, we work with this example, and I can maybe repeat this example 2, 3, 1. And then 8, 1, 2, 3. No, not 33.
The 21 or something?
Oh,
Yes.
-1, yeah. Thank you. And initially, we said the this array to -1. -1, -1, -1. Yeah. Then we see on this number, you see that there is no any increasing subsequence, and set that is the first increasing subsequence that we find. Yeah, but no. We need to set these numbers equal to plus infinity. Plus infinity. Etc. Yep. Then we see this number. It's equal to 3. And we find in this array place where we need to input 3. Because it is sorted array, and we find place by binary search. We spent log from number of log from n time to it, and we find that we need to insert here. So we change plus infinity to 3, and other numbers don't change. Then we see at this number, and we say, okay, we have this array, and we need to find place where we need to input this one. And we find here, but we have no number with -1. Yeah, with the iterator equal to -1. So we change to with it. So here we write 1. Then we see at 8. Find the place where we need to input. We find here, yeah. And so we change it to 8. Do you understand in which way? No. In each step, we find the place to insert new number. Using binary search. Extra, yeah. We can think, select it. Okay. No. So, let's try to understand what will be in the array after the next step. Here, what is the next?
1, 3, 8, 53.
8, 8, 4, 3. Nice. Okay, next step.
We add 21
Where?
after 53. No,
No.
no.
We change 8 to 21.
53. 21, sorry, yes.
Okay, next step.
Instead of 3, we put 4.
We change, no. We need to change not, not, yeah. You are right that we need to change 33 with 21 because the longest subsequence with that ended with 21, 2, 3, 4, 21. So yeah, we need to change. When we find the place, we change the right number with it.
So now we change 8 to 4.
Yeah, we change 8 to 4.
And then minus 2, 1 to minus 2.
1 minus 2, yeah. And then we say, okay, the number that is not equal to plus infinity is 21. It is the bigger number in this array that is not equal to plus infinity. So it is in the fourth place in this array. So the answer equal 4. Yeah. So it is in the common way it works similar. Yeah. Each step we find in this array place where we need to insert new number, and to find it we spend log from n time, and we repeat it for all the numbers, and so we spend only n log n time. Do you understand how it works?
I think yes.
Okay. Uh,
And here the memory will be n square. The memory.
time complexity and space complexity, or what?
Yes, space complexity.
Space complexity? No, it's equal to O from n because we spend only O from n to this array. But as you see, uh, time complexity. And here we get a space complexity equal to O from n because of store of our sequence. And of course, difference between this algorithm and the previous, that in the previous we store iterators, yeah, we store indices of we store lengths, yeah. What is the difference between third and second algorithm? Firstly, we see that third is quicker. So it is the improvements of the third algorithm that we got better asymptotical time to it. But in the second algorithm, we store lengths. And of course, it is integers. Always. It is integer. And in third algorithm, what we store? Not numbers. We store elements of the sequences.
Yes, that's right.
Elements. So, if you realize third algorithm in a way when we copy elements from the sequence in the fixed array, then if elements, yeah, we don't know what it is in common way. Yeah, in this example, of course, we find the solution of the task in which we talk about sequences of the integers. Yeah, and so we say that elements of the sequence equal to integers, and first array with name n was contained with integers, and this array fix also is contained with integers. But you can use these algorithms to find the longest increasing subsequence where sequence can be complicated with not integers. And in this way, you need to understand that when you copy elements from the initial sequence that you get in the array fix, you can spend additional time for it, and it can be very difficult for understand time complexity, because these structures that you can use for the elements can be very large, and so when you copy it, you spend more time than, for example, all this time for all the algorithms. Do you understand what is the... I think it is advantageous, the second algorithm that is disadvantage of third algorithm. But of course, I think we try to add it to the homework, but you can think about it. How we can improve it. Not to copy elements. In the third algorithm. In the third algorithm. Because now we say, or you see, we leave this definition. Question? Hashing? Maybe you can use hashing. You think about it in the home. At home, I think. And of course, you need to understand that initially this array full of numbers, am, and you need to change it to get speed up. Understandable? Guys in the Zoom, do you understand what is the difference in this way between in the end that by the definition fixed array contains elements of sequence, and you can improve it to change this array with different codes, for example, yeah, that you can use to hash your elements and not copy it. For example, of course, it's not only one solution to it. Guys in the Zoom translation, do you understand last discussion?
Yes.
Do you understand why we need to understand what is the elements of the sequence and why time complexity depends on it?
Time complexity depends on the elements.
Yeah, because if you use definition as on the board, you copy elements and you can spend a lot of time to it.
Sorry, we are talking about space complexity or time complexity?
Time complexity.
Ah,
Because when you copy elements, you spend time on it.
yes.
And if structure that you use for elements is very big, you spend a lot of time to copy it, and there is no interesting that you spend for the steps of the algorithm if you spend a lot of time to copy it.
Yes, understandable.
So it's all about the longest increasing subsequence and third. No. Third task that we talk about today. It's dynamic programming with the graphs. And I think graphs that we want to talk about today, it's trees. And there are different tasks that connected with dynamic programming and trees. And 3.1, for example, each vertex in the tree has its own number. Has its own number. As in the weighted graph. Yeah, do you remember it? Weighted graph. But vertices, but now vertices are weighted, not edges.
So the vertex has the same index as its own weight.
Yeah.
Oh.
As an example, I can write here. For example, this tree.
So we can have two times.
Hmm?
We can have the same number two times.
Yeah, for example, 3 is 3. And task is that you need to find the path with maximum sum.
And we have to visit all of the vertices, or we can skip some of them.
Please repeat. What do you?
Can you hear me well?
Now, yeah, I hear you. Well,
Okay. We have to visit all of the vertices, or we can skip some of them.
if we find, for example, this way, we need to sum all of the vertices in this way, in this path. And we cannot skip, for example, this vertex. We cannot do it. We sum all of the vertices in this path. Hmm? Oh. No. We can find, for example, this rows too. And of course, as we start earlier, what is the native solution?
BFS.
No. It's not DFS. How many paths are in this graph?
How many?
How many paths are in the graph? We know that in the tree, between two vertices, there is only one way. And so, how many paths in this graph?
N to the power 2 minus 1? No. It's for something else.
N minus 1 divided by 2. Because we can choose two distinct vertices. And we know that we find only one way between these two vertices. This one and this one, for example. So, why it is n? We can choose any vertex. Then we choose any other vertex. And then we say that we have no direction in the path. So we divided it by 2.
Sorry, once again, I didn't
Yeah.
understand.
Do you
The
understand?
reason that it's n times n minus 1 over 2.
Please
The
re-
reason of that formula. I didn't understand why the number of paths is n times n minus 1 over 2.
Okay, I can repeat. Firstly, what is the number of vertices?
And
N.
here in this example, okay, yes, no, n.
Arguments? See that if we want to find path in the tree, we need to find two ends of this path. First end we can find by choose any vertex. Then we can choose any vertex but not the first one. And then we say that we divided by 2 because there is no direction of the path. But of course, if you in other courses you say that we have direction of the path or what? No? Yeah. No? Okay. So you can see that this is equal to and choose 2. Do you faced with, or did you face with this number
Yes.
in the Combinatorics? And of course, you can see at this formula as you choose 2 vertices, and there is only one path that connects these 2 points. So, to native solution is to find all the paths and find the sum of these paths and compare it. Yeah. So how many time we spend on it? Time complexity.
Time complexity.
Yeah.
The number of
It is complexity. Complexity.
O of n squared.
O from n. What is here? Why you say n square? Because of number paths, yeah? But you can see that every path, a lot of paths can be equal to n by their length. Yeah, when we find the sum of the weights of the vertices in the path, we spend nearly n time for it. And we repeat it this time, n cube, yeah. In the worst case, we spend n power 3, because n power 2, it is asymptotical number of paths, and for several paths we spend nearly n time to find its sum of weights. So it is time complexity of this algorithm, and it's very big, because n can be billion, for example, and billion in third power, very big. So,
Professor,
of course,
I didn't understand time complexity. Why n cube?
because after we find all the paths, we need to find its sum.
Why? Why do we need to find the sum?
Because we compare summary of weights of paths and find the maximum.
Okay.
We compare not the length of the paths, we compare the summary of the weights in it.
Yes.
Because if we compare lengths of the paths, of course we need to find diameter, and you solved this task in the previous contests. But now we have weights in the vertices, and we need to use other algorithm. So we need to find sum, and we spend on it nearly n time. So it's native algorithm, and of course it's the worst case to solve it. And what is the dynamic algorithm? Dynamic solution. For example, we can see at the abstract tree without weights.
Schema weight between two subtrees.
Yeah, we can say that we can divide tree in two and solve this task for them. It's interesting, but we need to remember that there are different ways to find maximal path in the graph. Firstly, we can find maximal weight in a subtree, for example. Maximum path. In the subtree. Then we can find maximum path as the path that ends in the root. And of course, there is finally the most complicated case. What is the most complicated case? When we find the maximal path, not in this subtree, not as the path that connects vertex in the subtree with the root, but the path that connected different subtrees. It can be, for example, side path. Yeah. It is the third way. The maximum can connect vertices in the different subtrees. And so we need to store a lot of information to understand what is the maximum passes of each type. And then we got the answer at the maximum of 3 passes, that is maximum of these types. Solution. We solve the task for subtrees. And find the maximum path of each time. These steps, yeah? 1, 2, 3. And then we find the maximum passes for the roots of these 3 types, and then compare them and find the longest. So, about algorithm. Firstly, we make 2 arrays . First array is the maximum path in the subtree, and second array, it is the maximum path that end in the root of this subtree. So, one we say as answer, because for all 3 we get the answer. It is the maximum in the subtree . And second array contains passes that ends in the roots. We name it as RP, root passes at the maximum of the passes in the subtree that starts in the root. And of course, initially we have weights of vertices. So we understand how to divide our big task for subtasks to find results of the subtrees and then find new answer with these arrays. So how we realize this algorithm? For example, we have roots of our tree and we have subtree 1 and subtree 2. And I name adjacent vertices as U and T, for example. That is, they are adjacent to roots of the tree. So, we recursively find the values of the subtrees S1 and S2. Then, okay, if we have these three arrays, what we can say about the, for example, RP for the R? What is the maximum path that starts in the root? For example, we can say it can be a path from one vertex, R. So it's maximal of only weight of R. Then we say, okay, but it can be path that contains more than 0 edges. Yeah, for example, 1 edge, and other vertices must be in S1 or S2. And so, if we find
Can't it be in root?
no, it starts in the root. So we say that, for example, if this root will be in this subtree, yeah, we say that the sum of this path will be equal to weight of the roots and RP of U. Do you understand?
Yes. RP of
Mhm.
t plus we get
Yeah, it's roots. Yeah, and RP of t plus weight of root. So, due to other way to find this maximum path, yeah. So it's new RP for the roots. Okay, and the maximum of the paths in the subtree. How to find it? I need to find. Maybe we can copy this picture. No. If we clone it and nope. Unfortunately, okay. I write new tree. For example. Yeah. And to understand what is the answer of roots. What is the maximum path? Firstly, we can say that the maximum path may be only path consist only one vertex. Yeah, as in the RP. But as we understand that there are a lot of paths that ends in R, and we know the maximum of it. It is RP of R. So we can write here RP of R, not weight of R. Yeah, because it is the maximum of the paths that starts in the root. So, for example, it can be such path. Yep. Okay, and we know that maybe the maximal path in the graph equal to path that connects two vertices in different subtrees. Yeah, and how we need to find it? We can say that if it's U, yeah, it's T, weight of this path equal to, do you understand what is the weight of this path? It's equal to T, not plus but it's not true because we find these two, or if we find maximum of these two numbers, we find the maximum of the paths that contain root. But maybe the maximum paths, the maximum path doesn't contain the root. And in this way, this path must be in one of the subtrees. So after comma, but I can find, for example, maximum path as the maximum path in one of the subtrees. And in this way, we need to compare this maximum with maximum for each of the subtrees. And this maximum is equal to answer of U, answer of T. That's all. So it is the formulas of the RP and ANS. This way, in this way, we change these two trees, and then we find the maximum of the tree. And what is the answer of the algorithm? If you understand previous steps, you can say that answer for the task. What is the answer for the task? You can see here that answer tree of ans, it is the maximum of the paths in the subtree. And to find the maximum in the tree, we need to get ans of what vertex? Guys in the Zoom, maybe you? No? I can add that ans from vertex V. It's the maximum of the paths in the subtree with the roots V. And in which tree we need to find maximum of the paths. With what row? With what root? With what roots? With root R. Yeah? And answer for the task, it's answer. Yeah, but it's recursive formula for the subtrees, cos2. Yeah, when you go to the subtree, for example, S2, yeah, you can say that answer of T is equal to RP of T, etc. And here, yeah, you're right that. Yeah, it is the roots of the tree. As we see in each step, when we go down in this tree recursively, we spent uh, only constant time to arithmetic operations and comparison. So we say that space and time complexity for it it is equal to O from n and O from n2. And about space complexity, of course, we spent linear time, linear space to store n's and rp, but you need to understand that we need to store 3 trees now. Yeah, because this tree in our algorithm become tree with the complicated nodes. Each node have V, RP, and ans number. So of course, asymptotically, it's equal to O from n, but if we want to understand what is the coefficient before it, it will be bigger than in the native algorithm. But of course, time complexity is better than in the native algorithm. Guys in the Zoom, do you understand how we compute these numbers recursively, ans and rp, and why these two numbers, these two arrays, connect with the with our task. Masoud, Stefan.
Yes, it's okay.
I think, can we repeat the task again? Like, what is the goal of the task? What is the thing that we are trying to reach?
Try to reach what?
Yeah, the goal of the task. What is the goal of the task?
The goal of the task? Find the path with the maximum summary of weights in it.
Yeah, yes, I think, yeah. I think I understand this.
Okay, Masoud, do you understand? So,
It's fine, yes.
okay.
So the root have to be in the path.
The root can be in the path, yeah.
But it's not mandatory.
Yeah. Okay. So next, try to talk about second task connected with the dynamical programming and tree. We have time. Yeah, 10 minutes. Okay. Do you know what is a independent set? Of vertices.
No.
It is set of vertices that are pairwise unadjacent. Or disadjacent. I don't know. No adjacent.
So it's a set of isolated vertices? Or not necessarily?
I can draw the example. Pairwise, no adjacent, it's equal to there are no edges between them. For example, these three vertices will be independent center vertices because due to absence of the edges between them.
Yes.
So task finds the maximum independent set in the tree. And interesting about this task that if we change tree for arbitrary graph, then this will be NP complete task. Do you understand? Yeah. So it's very complicated to solve problem in the arbitrary case. But in the tree, we can find maximal independent set by dynamic programming, by dynamic algorithm. And do you know how to use dynamic programming to find independent set in the tree? As the previous task, you can remember how we find the passes here and try to repeat this algorithm for this task. How to find independent set in the tree? Firstly, it is main part of the dynamic programming. What we need to do? Yeah, we need to divide big task for some subtasks. And how we can divide it in the tree?
The maximum independent set in the tree is if you divide the tree, we will have the maximum independence set in the subtree.
Yeah, we divide it by finding the independent set in the subtrees, yeah? But it's not so simple. There are some problems with this. Okay. We can say that this subtree 1, subtree 2. We can find independent set for one subset or for the second subset. Okay, and you want to say that the maximum subset of the tree is the union of these independent sets. Yeah? But it's not true, because if you try to understand what is return value of this algorithm, you understand that your algorithm return only these leaves of the tree. And of course, we understand that we can add, for example, this tree, this node, yeah, etc. And how to improve this algorithm, not to get the false answer, to get the right answer in this case. We can see that there are two distinct cases of subtrees, of the independent sets in the subtrees. One case when we find independent set that doesn't contain roots, and the second case that contain root. One case. Doesn't contain root. Second case. Oh, I use difference. Contains roots. For example, for this tree, I can find this independent set as the independent set that contains and this independent set is the first case. So we add two arrays. Yeah. For example, independent set contains root. I think that it is understandable. Independent set that contains root. Second case. Okay. Second case, array. Yeah. And first case, array. And so if we have root connects with two vertices U and V, or U and C, and of course I draw always two subtrees, and of course we can have different numbers of subtrees, of course. It can be not a binary tree. But in the common case, it is similar to this rule. So, firstly, if the is leaf, do you remember what is it?
Yes. doesn't have children.
Yeah.
Yes.
So, first case, I write it shortly to spend my time. Our first case of v equal to 1. Second case of v equal to 1, 2. And then, if v is equal to root of the tree that have different subtrees, we say that firstly, doesn't contain roots. Yeah, first case, roots of 3 or subtree. We say that first case of R equal to doesn't contain root. So we can get union of two independent sets in different subsets. Yeah, it is second case of U plus second case of T. Is it understandable? And of course, if R has a lot of children, we need to summarize all of these children's. And second case, if we find independent set that contains root, we say that roots plus, yeah, plus we cannot add children of the root to the independent set because they're adjacent to the root. So we need to add all the maximum independent set that doesn't contain children. So we first case is the U plus first case was the T. And that's a recursive formula for the computing of the these two arrays. And then how to find answer for our question. What is the answer? Yeah, it is maximum. Of these two, F case and S case. And you see that. Oh,
R, I think.
yeah, R. Yeah, you're right. And you see that we repeat it for all the vertices, so time complexity is equal to O from number of vertices and space complexity too. So, as you see, the main is the summary of the lecture. Okay, you need to use dynamic programming in the way when you divide task in the subtasks, and as in the last undivided concurrence. Oh, divide and concurrence. Because I talk about it, but it is these two topics connected are connected. Divide task in the subtasks firstly, and then find recursive or dynamic connection between the subtask. So about next time we talk about other tasks that connect with the dynamic programming, and we talk about we work here with the trees and with the arrays, but there are two-dimensional dynamics. For example, for matrices, or we talk about added distance. Do you know what is the added distance? Added distance between two words. We don't know, and we talk about it next time. And we find two-dimensional dynamics in it. And we talk about I need to find two-dimensional, yeah, and other tasks, because there are several traditional tasks that you need to understand in the topic of dynamic programming. And in the end, I need to say that every time before you realize your algorithm, you need to understand what way is better to use your algorithm, in recursive way or in the dynamic way. We see now that in some tasks, when we divide it to subtasks, there is recursive equation between recursive equations appear, and in this way you can use recursive algorithms. But before it, we find different tasks that we can solve by dynamic algorithms and spend only linear time. So every time ask yourself what is the better way to solve the task, dynamic or recursive. And for today I think it's all. If you have any questions, you can ask. or if you have no questions, we end our recording.
Professor, is it possible to share the whiteboard, PDF of the whiteboard?